Good morning, everyone. My name is Tim Slater, and I'm from the University of Wyoming, and it's a real privilege to get to talk to you today. To look across the audience, it's a very interesting feeling for me. About half of you I know really, really well, and about half of you I've never seen before in my life. So if I tell you a joke you've heard before, I want everybody to laugh. That would make us all feel a little bit better. I spent the last 30 years focusing on trying to make a connection between cognitive science and the science of learning as related to how people learn and teach astronomy. And so what I'd like to do is to spend a little bit of time today sort of setting the stage for most of today's discussion, which will be very different in flavor than what you've done the past 2 days. So the first day was really about the technology of telescopes and where we are, where we can go, and what visions we can have. Yesterday was much more about what are all the different things we can do with these telescopes and what kind of successes we've had with students. What I hope today really does is begin to push you about making that connection of we have this amazing technology, we have these great things we can do with students, but I want to really begin to push you on this, how do we actually make that happen and how do we increase our footprint in the most effective way possible. In fact, what I want to posit to you is this question of if we have telescopes and we have great projects, should we actually use them? In other words, should we telescope or should we not telescope? That is the question that I'm going to pose to you today. So where I want to start is, many of you have notebooks or you have computers out. I'm going to take just about 30 seconds here, and I want you to say, what is it that I still don't know that I need to know about doing education with great projects and great telescopes? What is it you still need to know? Take 30 seconds and write that down. What do you not know yet? No cheating, Carl. Lisa has her own question. I know this problem. You already have the answer. Right? Don't tell anyone yet. All right. We're going to come back to that thing that you've written down here in just a moment. But I want you to keep an eye on that throughout the day, because there's an amazing amount of expertise in this room, a tremendous amount of success, but we haven't figured out a good way to connect these things yet. So I want you to be watching for the answer to your question as we go through today. All right, so here's where I want to start. We have, when we teach astronomy, an unspoken contract with our students. Unspoken and maybe even unknown. I mean, you may not know that you have this contract. That when students enter your class, whether it's a high school astronomy class, whether it's an introductory college astronomy class for non-majors, whether it's a course for majors, physics and astronomy majors, we have a contract. And what students expect is that your job as professor is to tell students stuff. Their job is to memorize everything you say, and on test day, give it back to you. That's the contract. If they are unsuccessful at memorizing everything you said, they get a bad grade and they're okay with that. If they are successful at memorizing everything you said, but you ask them questions on the test that aren't what they memorized, then that's a broken contract, and what happens? You get lousy student evaluations because you've given them a trick question. All right? This contract that we have with students is very frustrating if we break it. And so what that means is if you want students just to not memorize what you're teaching in the classroom, you actually want them to be doing science, you have to start out class by breaking that contract and helping students understand this is not what this class is about. And the reason I point that out is when students come in, particularly freshman students come to college, every professor they have says, this class is not about memorization. Whether it's their English class, their history class, their math class, their physics class, whatever. This class is about, I want you to learn to critically think in my class. Every professor tells them that. What happens in 9 out of 10 of those classrooms? They're a memorization class, exactly. So they have no reason to believe you when you say, this is a class about critical thinking, we're actually going to do science here. So you've got to start out by breaking that contract. Now, here's the setting that I teach in. I'm fortunate to teach in a very modern classroom. It's a sort of a reconceptualized design about how we should teach. I teach about 600 students at a time. No one's ever done this before. Well, there were some people in Turkey and Ephesus that did this, but this is a one-off. I mean, no place else like Greece has these sorts of things, like on the island of Delos. So it's a very modern approach to teaching. It's really, yeah, we have a lot of cool technology, but it's the same model, right? And what happens when I go out and we look at astronomy classes and we think about where do telescopes fit, particularly in that introductory science course, which is where most of us have the opportunity to have a really large footprint of maybe hundreds or even thousands of students over our careers. I really kind of see two types of Astro 101 classes. Did I need to lean sideways when the camera fell over? Okay. No apology needed. One type is the astrophysics class. These are classes that are taught not by people that are trained in astronomy or may even like astronomy, but have been assigned to teach astronomy. And their course, they view, should be a miniature physics class. This is characterized by this cartoon that says, you know, welcome to my astronomy class. Before we start, are there any questions? Of course, you always get this question, wait, what's the difference between astronomy and astrology? And the physicist says, oh, we do lots of math in astronomy. That's the difference. And of course, the drop rate goes way up and all the students leave and they hate the class. Kind of poking fun at the class. But we're talking about the person who designs their class around doing lots of things with calculators, using Kepler's third law, doing the law of gravity, having them calculate luminosity and flux. And that the calculators are a really important part of that class. The other type of class I see, broad generalization, is what I call the amateur astronomy class. This is the class where people are teaching star hopping, for instance. They're outside teaching the names of the constellations. They're not just doing constellations on the first day of class, they're doing constellations throughout. And to equally poke fun at those guys, that's the kind of class where, you know, you remember you're a graduate student and your professor gave you an image of the old Schmidt camera image of the globular cluster, you know the one I'm talking about, and you had to count the stars in the globular cluster. Yeah, I had to do that too. But the amateur astronomy version of the class is about let's get outside and let's look up, right? It's not just about talking about the night sky on day one. It's talking about the night sky throughout an entire class. I'm not suggesting that one is better than the other. I mean, in both cases, what we hope is that the goal is at the end of the course, students end up loving astronomy. They think astronomy is really, really cool and that maybe science is worth learning in the first place. And so how do we accomplish that with either model is one of the questions that's important to us here. Now, if we make this decision that, well, telescopes are important, whether you're teaching from the astrophysics position or you're teaching from the night sky position, you might decide that telescopes are important. Well, this is a real problem for many people, particularly people that are not trained in astronomy. Most people that teach astronomy at the undergraduate level are not actually trained astronomers. They're physicists by and large, sometimes mathematicians, sometimes geographers. But by and large, most Astro 101 courses are not taught by trained astronomers. If you look at the Astronomy 101 textbooks that are out there, and there are some really great ones, for example, those written by these authors up here. Those are all mine, Carl. Yeah. There's telescopes are in there, but nothing about how to use them. Those resources just don't exist for most people that are out there. So as you think about your projects and think about expanding your footprint, increasing the number of people that are using your projects or using your instruments, you have to realize there's very little support work out there. And this is particularly true if you work in the case of K-12 teachers, where we've trained using NASA's pumped $50 million per year into education for astronomy for decades now. And the number of those teachers that we've trained to use telescopes, they're still using telescopes, is teeny, teeny, tiny. There's a huge disconnect in our education world about getting stuff from the development stage into the actual classroom stage where hundreds of thousands of students are using these sorts of things. That's a real, when I write down my questions of where do we still need to know, that's my question. How do we deal with scalability related issues? All right, so let's suppose that you do in fact believe that telescopes are something that should be included in the astronomy class in education. What I want to know is why? I want you to take a piece of paper you've been writing on or your computer or your phone if you want to make a note. And I want to know 3 specific reasons why one might think their student should be using telescopes. You've got 1 minute, go. No, you can't talk to your neighbor. Dave, don't cheat off Lena. Three specific reasons. Now she gets a pencil out. I gave you the clip at the beginning, right? It was anticipatory set and everything. I won't steal your thunder. I promise. But I'm going to step on you. I'm not set you up. All right. What I'd like you to do at this point is I'd like to turn to the person next to you. If there's no one sitting next to you, turn to the person behind you, and see if you can convince them to tell you at least one thing that they've written down. Go. You get noisy in here. You behave, Mecca. I'm not buying you any more coffee.
We're totally engaged. We're like love one mind, so we probably should split us up.
There's time yet. All right, time. Okay, so I need to get a sense of what people are talking about. So just kind of in the 1, 2, 3 word sort of rationale, let's do what I call popcorn. Just sort of sound off here. Somebody from this group, what's one thing? Engagement, good. How about this group? Eureka. Am I going to ask you to explain that one? No, I'm not yet. What? Variation in data, good. How about this group? Ownership, good. Motivation. Correlation. Sexy hook. History. Mystery. You said earlier, right? So mystery. I'm getting a theme out of you. All right. Problem solving. Anti-black box. Right? Yep. Learning despite the teacher, in spite of the classroom. Right? Now, as I was listening to you guys talk, what I was hearing you talk about things that weren't astronomy specific, but were more science in general related. I mean, could this same conversation be happening among a bunch of chemists? Well, no, let's not say that. A bunch of geologists? Yeah. Yeah, got that one. Well, I mean, what if we're talking about learning science in general? What does that mean? Well, the National Research Council spent a lot of time and energy talking about students that are proficient in science. What does that mean? And they broke it down into 4 things. Those of you that are into writing proposals, this is definitely the list of 4 you want to have. 4 things, and this is from a book called Taking Science to School. The first one is that students that are proficient in science know how to use scientific explanations. The second thing is they're able to generate scientific explanations and evaluate scientific explanations. None of this is about memorization stuff. That they need to understand how scientific knowledge comes about, how it's developed. And this last one, I think, is the place where robotic telescopes and remote telescopes have the most chance for influence, is that students who are proficient in science participate in talking science. They know what scientific discourse looks like, and they do it. They don't just listen to it. They do it. And this is a real opportunity for those who decide to telescope rather than not to telescope, is that students can begin to talk science, if you teach them how. Students don't naturally know how to talk science. We do because we do it all the time. Some of us have spent 5, 6, 10, 15, 30, 45 years talking science, right? 18-year-old students don't know how to do this. And so we do have to take time to teach them. And telescopes seems to be a great place to teach students how to participate in scientific discourse. All right, so let's suppose we do decide that you want to teach science through teaching telescopes. There are a couple of ways to go after this. So one is to take the perspective that students should learn about science by watching and listening to a wide diversity of scientists talk about what it is that they do. The other approach that's equally as good is this idea that maybe students should not be listening to other people talk about science. Maybe what they should be doing is mimicking what it is that scientists do. Now, both of these things are really, really hard to accomplish on their own. Accomplishing both is nearly impossible in 12 months' time. You really do have to kind of pick one. And if you're not picking one, you're just randomly doing what you think might be a good idea, your next proposal is not going to get funded. Because what we understand now in the education world is you really do have to have a theoretical reason for doing what you do. So, suppose you take this approach that students should learn about science by watching and listening to what other scientists do. For example, you might think about the debate about whether the debate about whether or not the Andromeda Galaxy was the Andromeda Nebula or the Andromeda Galaxy. Right? And you might like to have students participate in that debate and reproduce that debate. Well, I have to tell you, to do that right, where they're not just memorizing positions, but actually thinking about it, actually discovering it, takes a tremendous amount of time. This is not something you do in a half an hour. This takes weeks if you want students to be able to discover the difference between a galaxy and a nebula. Is it worth doing? I propose it could be. In fact, I think it is. But that's going to take a lot of time away from other stuff. When you could, in 30 seconds, just tell them, hey, back in the 1920s, we weren't sure what that fuzzy thing in the sky was until somebody found a star in one, and boom, we knew what it was. You can either do that in 30 seconds, or you can take the weeks it takes to have students discover that. You can have students discover gravity or inertia, if you will. If you're into discovery learning, that's what that looks like, and it takes time. On the other hand, suppose you think you want to take the approach of students should be doing science by mimicking what scientists do. Well, there's a variety of ways to go after it. Maybe you think that students should be doing original published research. A perfectly viable option. Or maybe students should be doing classic observations. Figure out the orbital periods of Io, Europa, Ganymede, and Callisto, for instance. You don't have time to do both. So you need to be making very conscious choices about which way you want to go with this, because time is really, really an issue, particularly if you only have students for 16 weeks or a year. If you've got 2 or 3 years, that's no problem. But most of us don't have that kind of interaction time. Maybe we've got 12 months at the most if we've got a really well-funded teacher education program. So one of the things that this team over here brought up was this idea of ownership. And ownership is something that, as we sit around in the after-hours lounge and drink way too much beer, that we really wonder about what does students' feeling of ownership have to do with this? How important is that students own their data? I mean, you might just think, well, we'll just ask the classic question. We could do this from an educational research perspective, right? We could give students 2 pictures, a picture they took and a picture that maybe came from the Hubble Space Telescope, or in this case from the Cassini, and say, which do you like best? I mean, it sounds like a pretty easy educational research question, doesn't it? Turns out when you do this, and the reason I know it's not easy is because I've tried and failed miserably, is when you do this through interviews, you get all kinds of crazy answers that really sort of sits on the it depends. Well, that's not very satisfying, right? If you're trying to make the decision of, I've got this beautiful 2-meter telescope, and I got the 1,000th kid that wants to take a picture of Jupiter, should I let them do that or not? Right? It's a real question. I mean, you may have your own personal opinion about that, but what does the kid really need? It turns out this is a really, really messy question. So to make it less messy, we tried this experiment again, but we made it multiple choice, so the answers were really easy to analyze. You can do a t-test, and even do an ANOVA statistical analysis on it. And it turns out that this question is still a mess. Students that say it depends in an interview will choose A or B and not tell you it depends. So it turns out this, from a research perspective, this question's crap. Doesn't get us anywhere. So we tried another question. We said, well, wait, maybe if it depends on what they're using it for. So we asked the question, if you got the professional picture and the amateur picture, which one's more useful to you as an astronomy student? Because it turns out the way you pose the question really, really matters. Because unintentionally, if we think there's a right answer, if we think that our project is really, really cool, and of course it changed students' lives, we will often get the evaluation result that we're wonderful when in fact we are not. Because the way you pose the question matters. So we tried a different approach here. We said, all right, went back to what we did with lecture tutorials, went back to the idea of the micro debates. And we said, all right, you've been doing this telescope project where you took images, right? Now imagine you're listening to other students talk about this remote telescope project you've been doing. And Leonard says, you know, I like this image that I made because I took it, I made it. And Rachel says, well, I like the image from the professional best because, well, it's crisp and clear. And Rachel, being the magnanimous person she is, she turns to George and says, George, what do you think? And George said, I don't know. We asked the students, you overhear this conversation, who do you agree with? Now, make a quick prediction in your head. What do you think most students say in your head? Turns out, most students would agree with Rachel that I need that professional image because it's clear and it's crisp. Now, that flies in our face of what we've been thinking about ownership. When students take the time to go out and figure out how to take a picture, yet we think they like that better, yet when they look at this, they say, oh no, I need the professional picture. Well, that's kind of depressing for a lot of us who spend all this time and energy trying to get our students to create their own image. But from the previous slide, we learned that how you ask the question matters in ways we don't always understand. So we said, let's just try something different still. We asked the question, all right, suppose you're going to show a friend or a family member a picture of the planet Saturn. What picture would you use? Would you use the picture you took, or would you use the picture that came from the Cassini? Here's the data, even. In one case, we're asking about a classroom thing. Another thing we ask about, what do they value? What do they think is most important? So this question of ownership is completely unknown to us. My gut tells me, just like you guys, ownership is important, but we have not been able to statistically prove it in a really robust way because it depends. And this also influences this debate that many of you are having about, is it best for students, when I first started working with students, should they be using robotic telescopes where they're controlling it, or, well, I forget which is which, or remote telescopes where the computer is controlling and putting into a batch queue mode? Oh, did I just get them backwards? Yeah, I do that all the time. I mean, which is it, right? Which should you, if students are, you're really trying to engage students and eventually loving astronomy, should they be driving the telescope or should they be telling the telescope what to do? We don't even know if they like their own picture or not. Trying to uncover this question about robotic versus remote is really, really ugly. We don't have a lot of theory that guides us because science education is just like astronomy. We should have theories that tell us a priori, before I ask the question, here's what the answer is going to be. I mean, when you have telescope time, take you some hotly competed telescope time, you don't just say, oh, I'm just going to go look at stuff. You've got to have a real reason for what you're looking at and why you're looking at and why you need that valuable telescope time. Science education works exactly the same way. You've got to have some sort of theory that drives why are you doing what you're doing, particularly if you want to get funded from the National Science Foundation. You've got to have a cognitive scientist on your group to do that. And if you're not being funded and you don't really understand why, this is because often what the work we do, and I've read hundreds, if not thousands at this point, proposals. You've got to have theory that drives where you're going with stuff. I mean, I love remote observing. I hate going up to Mauna Kea because every time I go up there, and I live on the side of Mauna Kea, every time I go up to Mauna Kea, I puke my guts up. Can't do it. When the invention of being able to do this from a laptop computer came up, I was pretty excited about that. But what is the best way? Do students need to be driving the telescope? Like this is Scott Mecca and Dave McKenna here working on Sky Titan project, which you'll learn about later today, where students are driving the telescope from their home computer in real time. We don't know the answer to that. I mean, at this point, we don't even know if most teachers or even professors believe data mining counts as doing science. There are many, many science fair projects that don't score high because the student didn't collect data themselves. And people, even familiar with science, even familiar with physics and astronomy, don't believe in archived data. In fact, getting your students to believe that they can do science off archived data is really, really hard. The lab project we've been working on with archived data, it's really, really challenging to get students to think they're doing science if somebody else collected the data. Now, geologists, they get this, right? Because geologists never get to collect their own data. The Earth collected it for them. They understand that part. All right, so what theory might guide us? So I've been pushing on this idea of what's called a learning progression. And learning progressions is the theoretical model that was used to develop the NGSS. And whether you like the NGSS, the Next Generation Science Standards, the K-12 framework for teaching science in the United States, that you have to say you're addressing when you write your proposals, even if you haven't read it. I know, me too. Use this idea of learning progressions. I'm not convinced that they're really, really the right thing, but what happens when we try to apply a learning progression to this? Now, the basic model of a learning progression goes from student thinking from what we call the low anchor to the high anchor. And the low anchor is what students should know what you expect students to know and understand and believe in their gut when they walk in the door. And the high anchor is where you're trying to get them to and all the steps in between. So you can't read that, so let me do a bigger version. So I propose that the lowest anchor, where you can believe all students are walking in the door, probably starting in elementary school, is those little white dots in the sky are called stars. There are these stars in the sky that you can reasonably believe that students know this. Now, not all, there are exceptions to this, but I think that if you think that's the starting point, the lowest anchor, you don't have to teach students this, all the way up to what does the upper anchor look like. And I think our uppermost anchor, where we can get to in a reasonable amount of time, maybe 24 months, is that detailed analysis of astronomical objects can be accomplished using telescopes that are robotically controlled or by data mining. And I think you can't get there in 30 minutes. I'm not even sure you can get from there to there in 16 weeks. So, what are some things in the middle here? Well, one thing is that students don't already know that there are things that are visible in a telescope you can't see with the naked eye that are close by, like planets, like Saturn's rings. And students totally don't know, unless you teach them or they have experiences, that there are objects that are very far away that can only be seen in telescopes, including stars. And students have to have experiences that get them to that point. I think, now this is my gut, someday I'm going to get the data that actually solves this. I think students need to drive a telescope before they can use a batch Q telescope, before they can do data mining. I think students, once they've had that experience of pointing a telescope and getting some data, then they're okay with letting the computer do it for them, but not until they've had that experience themselves. And students will not think that data mining is real science until they've used some data that they've told a computer to go get themselves. But once they've had this experience of telling a computer to go get it, they're okay with using the computer collected data that somebody else told the computer to go get, like the Hubble Space Telescope, for instance. Now, this is my theoretical model of the direction that things are going, and a lot of work is going to have to be done to demonstrate whether or not this holds out. But everything I know about educational research, educational psychology tells me that that's the right direction. You can get students to start doing science immediately with data mining by mimicking what you do, but do they really get it? I'm not convinced they do. What's the difference between driving the telescope themselves and having the computer drive the telescope? I don't think they believe it's real until they've had the experience themselves of telling a computer to go drive it. We don't have the data for this. This is a proposed learning progression, and it may be completely wrong. But I think this is the place to start. The students need a series of experiences in order to get here. Now, there is a risk, and there's risk of cognitive overload. If we have to teach students that there are planets out there, and there's the nebula out there, and there are galaxies out there, that's going to take time. Maybe time away from all the research projects we could do, finding really, really cool asteroids or finding supernovae. But I think we're going to have to do it for the vast majority. I mean, if you only want to work with the 6 smartest kids in your school, then you can probably just tell them that and they'll go, yeah. What if you want to work with the next 6 smartest kids, or the next 1,000 kids, or the next 10,000 kids? Our models of working with just with the brightest kids aren't going to work. We're going to have to be much more slow and much more deliberate in our presentations here. Because there's just a lot of stuff when we talk about robotic telescopes that we've got, robotic telescopes. All right. I think there is a working solution that we've got in place. It's not perfect by any means. And it's a solution which we call backwards faded scaffolding. It was developed by Stephanie Slater. And the idea behind backwards faded scaffolding is students need lots and lots and lots of teeny tiny miniature learning experiences all strung together. And early on, the students need a lot of hand-holding. They need a lot of structure, a lot of direction, a lot of modeling. And over time, we can begin to release how much structure and scaffolding we give those students. And they eventually can do their own research projects. But they got to remember, it takes time. You can't do one experiment, one observation, and say, okay, now you guys go do it. And what Stephanie would argue is that it takes many, many of these, 40 or 50 miniature observations over a course of a 15 or 16-week semester. We're piloting this right now at Penn State. I'm working with Chris Palma and Julia Kregenow in a project which is beginning to show some real results, working with hundreds of students, not tens of students. It takes a lot of time and a lot of effort, but it helps solve the scalability problem, which is where we're going. For example, we've been doing this with Galaxies Zoo. Galaxies Zoo, those of you who played with it, is one of the most successful of all time citizen science projects. All right? 250,000 observers doing 50 million observations in a 12-month period. Huge, enormous. But students have to figure out that that data is real, even though it's being delivered to them by a computer taken by a telescope that they haven't directed. They don't think that they're doing science with this. When you ask them, is this science? No, no, it's not science because I didn't collect the data myself. All right, so what? Where are we going with this? When you're thinking about the wide variety of things that you do, some of you teach high school, some of you teach Astro 101, some of you work just with astronomy majors, some of you work with pro-am collaborations. If you've got a lot of astronomy to teach, and telescopes may or may not be one of those things, what I will tell you is this, that I've learned over the years, you only get 5 things. When you decide what you want to do with your class and whether or not you should be teaching with telescopes, you only get in a 16-week class 5 ideas that you can successfully teach students. And you got to pick those 5 and you got to believe in them, you got to believe passionately in them, you got to teach the hell out of those 5 ideas. Not 6, not 7, 5. That's all you got. Because these are 5 ideas that you want students to remember 5 years from now. Students may not remember the magnetic declination of Saturn or the density of the sun at the core for 5 years from now, and you're okay with that. But there are at least 5 things you want your students to know 5 years from now. And those are the things you should spend your time and energy on. Because for a student to learn one of these 5 ideas really deeply, they've got to experience it 5 different ways. Now is the number 4, is the number 6, I'm not sure. I got 5 because I got 5 fingers, so it's easier for me to count that way. So as you're making your decision about how much time do I want to spend using remote and robotic telescopes in my education class, is it one of your top 5 things you want students to really, really understand? And if so, you need to have students interact with that telescope 5 times. Because the first 4 times, they're still trying to figure out which end is up. You can't just give them one modeling experience to tell them to go do it. You got to do it again and again and again if you want it to stick and last, which I think is what you guys really want when you're talking about education. You want long-standing change of their lives. Thank you very much. I thought I ran it so you wouldn't have to get to ask me any questions.
So I want to ask you something about the question, the ownership question that you were doing.
Where are you? Oh, hey.
And that is what was striking to me about the various ways you were asking that question was that in none of them was the student observation or image something that was really being used to do science. It was just a pretty picture, right? And my suspicion is that if they were actually using that data, you'd get different answers about which one they liked better and so forth. If they were answering a question that hadn't been answered already using that data.
Right. So, but what's your prediction, right? If they've taken their own image and they've got it, and they're doing real science on it, and they realize, just like Russ said here, the data is messy, right? There's a lot of variability in that data. You know, having some clean data from Gemini would be a good idea rather than something they took themselves, maybe. The value in having some really good high-tech data that came from some place or something that they took themselves. Yeah. Mm-hmm. Russ, you want to add to that? Well, this is one of the things that we see in the Galaxy Zoo data, is you had many people that were not publishing their work, but the fact they knew they were doing something that was contributing to scientific work, they found incredibly valuable. They didn't want to be just wasting their time playing a video game. They wanted to actually contribute. So I think that's consistent with both of those. But what I hope you take away from this is that it's fuzzy. It is fuzzy and tough.
I'll follow up on that. You can tell you touched a nerve with those pictures.
Oh, yeah.
I think part of the question for me is not what they find valuable or what they like, because if I use that as a guide to all my classes, I would never make them write anything. They don't find it valuable. They
True.
hate doing it. They love all my hands-on experiments and they hate writing them up. And I get that feedback every year. I think that we want to foster this joy in science and joy in learning science. And it's hard, like we have to temper that with what we as educators think is important too. So it's like the actual question itself becomes also fuzzy.
So I'm not going to disagree with you because I like what you've said here. But what I want to push back with you is on what do you do with the funder who's given you $1 million and says, I just put $1 million into this telescope for you. Now, I don't want all your students taking pictures of Jupiter. There's already great pictures of Jupiter out there. Let's do some real with this, right? And as an educator, you got to step back and go, wait a minute. Is it important that students take that picture of Jupiter or not? And the answer is we totally don't know. I mean, we spent a lot of beer time working on this as well as looking at the literature. It's not clear what you tell the funder in that situation.
Okay, going over to Scott.
Tim, one of the things I think I'd like to have you address is the perceived STEM crisis in America and everything that we're all doing here, how to address it and fix it.
In 30 seconds or less.
Yeah.
Boy. Well, so this is a question like, when did you stop beating your wife? Question. Because there are some huge STEM crises in the country, right? Is astronomy one of them? I mean, of all the scientific fields, astronomy has the lowest rate of unemployment, right? Anyone who got a PhD in astronomy this year got a job. Maybe not doing exactly what they wanted, but they got a job. Often on Wall Street, where they get to wear great shoes and have great hours, or in a hospital doing medical imaging technology using all their numerical recipes that they've learned. I mean, is astronomy, I mean, if you had $50 million a year to help the STEM pipeline, which NASA has been piping in, you know, would you put it all in astronomy? Is that the question you're asking? That's a way to get really unpopular really quick. I love astronomy. I think astronomy is a fantastic way to engage students. It captures their imagination, the awe, the mystery of things. But I'm not sure that our job is to make more astronomers. I'd like to get some really good doctors out there, some great biochemists out there as a result of my work in astronomy. That's unpopular. See, he's cutting me off.
Now it's going to go in one question, and then we'll move on.
Question, Scott. I don't mean to be flip about that answer. It's tough.
JPL. It's a gateway.
It's a gateway. Astronomy is a fantastic gateway drug.
Doing things. I've seen this for the first time. If I can get this done, and you actually start figuring out numbers and realizing what's going on.
I mean, if you were a vacuum tube physicist, wouldn't you use astronomy to get people to become more vacuum tube physicists? I mean, would.
Yeah, that's where you're starting. I mean, if you're starting with someone who doesn't know anything about anything, then you
that's
really
right.
know this is a way to get in.
I'm 100% in agreement with that. And I think that your proposals will be more successful if your angle is we're trying to increase the STEM pipeline, not make more astronomers. Because there aren't just astronomers reviewing your proposals. I think you're going to be more successful in that way. That's great, Glenn.
Okay, that's all. Thank you, Tim, for